So the next thing is shear stress distribution. So Tom Joseph. Yes. So what is shear stress, Tom Joseph? Stress is force per unit area. So what is shear stress? Shear force per unit area, that's all it is. Okay, it's essentially nothing but the viscous forces. So we want to calculate how is shear stress distributed, and looking at that is going to be little more useful because it will tell you, some nice detail about the flow. So can you calculate? So what is the relevant shear stress that I will have? So shear stress is, has how many components? It has 9 components in general in a 3D system. Okay. So because we are talking about a cylindrical coordinate system, we will have tau r, tau r theta, tau theta theta, tau r z, and so on. Okay. The only shear stress that's really relevant for us is here, because you have u z as a function of r. So the only shear stress that we need to really care about is tau r z. Okay, because the velocity, how is tau r z defined? Okay, so let's see. Santosh, what is Newton's law of viscosity? So that's all we need to write. The stress is equal to viscosity times the velocity gradient. So that means tau r z is nothing but mu times dou u z divided by dou r in this case. Okay, and that will be a non-zero quantity because u z is a function of r. Anything else you are going to take most likely will end up being 0, okay, or a constant. So that's the quantity. So can you go ahead and calculate what it is? That now we know what is dou u z by dou r. Right? You just need to differentiate it with r and multiply with mu. You get something like that. Okay. So that means the shear stress varies linearly in the pipe. Okay. The velocity varied quadratically. The shear stress is going to vary linearly in the pipe. So if these are walls of the pipe and this is at the center, you will find that it is basically going to, so what will be it at the center? What will be the shear stress at the center? It's 0. Why is it 0? Because you have an r max, you have a velocity maximum there. So dv by dr has to be 0. That's why the shear stress is 0. Okay. So shear stress is 0, and then it will it will increase with a negative sign linearly towards the wall. So that's how really the shear stress distribution is going to look like. So this is really, so that's my r, this is my pipe, okay, that's my velocity u z, and the profile would for tau r z would look like that. Any doubt? Lakshita? So shear stress at the wall, tau r z at r is equal to capital R is r by 2 into dp by dz. Okay. So, this is really the shear stress at the wall, and this is known as wall shear, and it is an important quantity because that is what actually is resisting your flow. You are actually pushing the fluid with a pressure gradient, the wall is opposing it. The wall is opposing it by applying a shear stress on the fluid with a magnitude that is r by 2 into dp by dz. Okay. So, typically when you want to talk about a force that is resisting your fluid motion, it is really the wall shear. Okay. Now, that is true now in case of a laminar flow, and this is a quantity that is going to change when you are going to talk about other flows like turbulent flow, or we will see few more examples later, but wall shear is actually an important quantity. That is also clear. So, let us this equation, right, tau r z equal to r by 2 into dp by dz. Tau r z is equal to r by 2 into dp by dz. Let us write down that from a shell balance. So, you have done the shell balance approach in your continuum mechanics. Is that simpler than what we do here, or was that difficult? It is actually not very hard. Let us just do a quick one. Okay. So, we have fluid flow through the cylinder. The reason I am trying to do that is because it gives you a little more insight on what is happening. Let us say the pipe, okay, and let us consider a cylindrical fluid element. Okay, a cylindrical fluid element of radius r, of length let us say small l. Okay. You have applied a pressure gradient. So, let us say on this side the pressure is P plus delta P, and on this side the pressure is P. Okay. And what happens, because it is basically in a fluid, the surrounding fluid will exert a shear stress on the cylindrical element, which is exactly going to be tau r z, which is acting in the opposite direction everywhere on the surface of the cylinder, right. Then you can say that, oh look, so my forces should balance, and therefore, so here it is P plus delta P, here it is P. So, only the differential pressure, which is delta P, is going to be acting on the fluid element, which is delta P, and if I multiply with the area, which is pi r square, that is going to be the force coming from my pressure difference, has to be equal to what? Tau r z, which is again force per unit area. So, I should multiply by area in order to get the force, but it is acting on the circumferential area. So, which is going to be 2 pi r l, and with a negative sign because it is acting in the other direction. So, what happens if you simplify this? Pi will go, r will go, I get tau r z is equal to delta minus delta P divided by L into which side am I taking? Yeah, okay, tau r z is equal to into r, right, by 2, correct, and minus delta P by dl is what we call as dp by dz into r by 2, and that is what exactly we derived a little while earlier there. Tau r z is equal to, okay. So, it is one and the same thing, that is what I wanted to tell you, that if you had actually started from a shell balance, you would have ended up with the same equation. You would have written down this equation, and then you would substitute tau r z using Newton's law of viscosity. You can find out then what is the velocity profile. That is clear. Look at this force balance. This force balance tells that any fluid element you are going to see, okay, it experiences a force because you have applied a pressure from one side. So, the fluid element is actually trying to move in the in presence of the rest of the fluid, but when it is trying to move in presence of other fluid elements, it is experiencing a shear stress in the opposite direction, because viscosity does not like things to move with a differential velocity. Viscosity does not like that. Viscosity will try to resist it. It will try to resist it by applying a shear stress. Okay. So, pressure is trying to push it in one direction, the shear stress is trying to push it, push it in the other direction, and that fluid element therefore is in a equilibrium state, where it's not being acted by a net force, but it is still continuing to move, because we have already assumed it's steady state. So, it's moving with a steady state velocity. So, that's what is actually happening. That's clear? So, it's just a convention. Okay. So, so in this pipe we are saying that this is going to go that way, that means the pressure you have applied is larger compared to here. Okay. So, in this direction we have pressure that is decreasing. Okay. So, when we define dP by dz, this was our positive z direction. So, dP by dz is just, or other way to think about it, it is really P minus P plus delta P divided by L, because the pressure on that side minus pressure on this side. Depending upon whether you want to talk about whether the fluid element is exerting shear stress on the fluid outside, or it's the other way, there exists one convention. There also exists another convention in which whether you want to interpret shear stress as a force or momentum flux. Okay. So, the minus is essentially to do with that. But the point is that when you consider a fluid element, pressure is the one which is going to push the fluid on the right side, shear stress is the one which is going to push the fluid in the other side, and it's a balance of that. Okay. We will do quickly comment about pressure now. So, I kept saying that we will always do this. I mean, I have been doing this with the horizontal pipe, right, and many of you actually had this concern that why aren't we talking about gravity, and I kept saying that okay, let's talk about horizontal pipe, let's ignore gravity, but gravity is always there, the pipes need not be horizontal, okay, and you know that we have gravity present in that equation, but we need not solve again, because there is a nice way of interpreting things. So, let us just look at that interpretation and before moving on. So, we will start with again Navier-Stokes equation, but we will stick to Cartesian coordinates because that is simple, and we will just look at a 1D equation. So, x momentum equation, how does it look like? Dou u x by dou t plus u dot grad u x is equal to minus dou p by dou x plus mu del square u x plus rho g x, where g x is the component of gravity acting along the x direction, right. If fluid is static, then what happens? All these terms will go away, though this Laplacian will not remain, and you get dou p by dou x is equal to rho g x, or if you integrate, that will give you that p equal to some integration constant times rho g x x, right, the equation that you are very familiar with, and this pressure is called, this is an example of hydrostatic pressure, because this is developing hydrostatic pressure due to gravity. What does this expression tell you? Siddharth Singh, what does this expression tell you when you look at it? How do you interpret? One is that pressure varies linearly with height, one of the thing, yeah. The fluid is not moving, still there is a pressure gradient, right. because of the weight of the fluid. Okay, weight of the fluid. So it's as if there exists a pressure gradient that supports the weight of the fluid, and that's what gives rise to buoyancy forces and so on, right? So what we can do is, we can say, so what our intention right now is to take care of this gravity, and what I am going to do is I am going to bring this gravity in defining a pressure, and that pressure is called dynamic pressure. PD is defined as P minus rho g x times x. So what am I doing? I am defining a new pressure that's equal to P minus rho g x x. Okay. So what is then dou PD divided by dou x? That's simply equal to dou P by dou x minus rho g x, and therefore if I look at this equation, I can say that it's rho into dou u x by dou t plus u dot grad u x is nothing but minus dou p d by dou x plus mu del square u x. Agreed? Okay. So dynamic pressure essentially is defined in order to accommodate gravitational force, and this is the equation in fact that we solved throughout, right? So the pressure that we have really calculated even in presence of a gravity was really the dynamic pressure. If you get dynamic pressure and if you want to talk about the total pressure, now you know the relation, you can use this relation and find that, you know, my total pressure is going to be nothing but my PD plus rho g x times x. So that's a way to easily accommodate gravity without really caring about gravity. Is that clear? So what would it look like if you write down, let's say, velocity profile for our you know, pipe flow? Can you write down Vz explicitly into, so what is the, so we got Vz is equal to what? Some r square divided by 4 mu something, no? 4 mu into minus dp by dz into 1 minus r by r whole square. That was the expression. What pressure is this? Will this be absolute pressure or dynamic pressure? This is the dynamic pressure that we really used. So can you substitute for in terms of absolute pressure and gravity, what would that mean? That's what it's going to be, right? That's all it is, okay? So this is nice because let's say you consider two walls and then there is fluid in between. Okay, this side is P atmosphere, this side is also P atmosphere. That means dP by dz is 0, you only have rho g z, because of which it's going to develop a flow and the fluid is going to go down, right? That's all it says. On the other hand, if you had applied a pressure gradient in this direction, let's say by putting something below like fluid in a container, then what are you going to do? You are going to apply a upward force, okay? You are going to apply a dP by dz upward, and these two terms will cancel each other when dP by dz is exactly equal to rho g z, in which case there is no flow. If dP by dz is more than the rho g z, then there will be an upward flow. That's what it is. So it's really that competition that these two terms are showing. That's also clear. Next problem.